Welcome back, Physical Science 20. This is the fourth video. We just started this example. Let's look at how we're going to do that now. So over here, Q equals MC delta T, and here, Q equals MC delta T. So in a particular phase, liquid or gas, we use Q equals MC delta T. And in this part here, vaporization, Q equals MLF. All right, so we're going to have three different calculations, and then at the end we're going to combine all that together. Okay, so if we look at this first phase here, now I have to be careful here because it turns all into vapor, but we're not told what temperature we reach there. So we have to back up the truck here a little bit. Since we're not told if it turns into vapor or how long we're in the vapor phase, the question does say it turns into vapor. So that likely implies that we've just reached the end point here. So we've just reached the point in which all the liquid has turned into gas, and we've reached here. So actually there's two phases we're going to be doing here. Since we're not told anything else about does the temperature go up when it's in the gas phase. So we actually have two scenarios here. My mistake. So let's look at the first phase. We'll break this down into the liquid phase and then the liquid to gas phase. So in the liquid phase, Q equals MC delta T. So it has a mass of 0.135 kgs. The specific heat, the C value for ethyl alcohol. So for that, of course, we have to look back at this chart. Now I'll try to get you a paper here having all this on one page so you don't have to flip back here. So the C value for ethyl alcohol, 2.46 times 10 to the 3. 2.46 times 10 to the 3. Okay, and our temperatures, we started off at 21, ended up at 78.3. So of course we know that delta T is equal to final temp minus initial temp. So my final temp, 78.3 minus 21.5. So I just did that all in that one step right there. So with that, so 78.3 minus 21.5, 56.8. Multiply that all out, 18,863.28 joules. All right, so that's what I get there. So we've covered this part here, the part involving just liquid heating up until it starts to turn into a gas. And in that phase, of course, Q equals MLV, vaporization here this time. So Q is equal to the mass, 0.135, and I have to look up the LV value for ethyl alcohol. Ethyl alcohol, going from liquid to a gas, 8.6 times 10 to the 5. 8.6 times 10 to the 5. And that's going to give us 116,100 joules. So there's my two energies involved. And then, of course, to find the total thermal energy, so I can do that down here. So total thermal energy, take what I have here. Notice they're both positive because we're absorbing for both. So 138,963.28. I'll round it off to 3 sig figs because I think that's what we have in the question. So 135,000 joules. Or of course you could put it into scientific notation. Put the decimal here. 1, 2, 3, 4, 5. Either one will work there. All right. All right, let's look at this next one. This next one is a common one. It's water. So we know water, and it is freezing. No temperatures are given. So, of course, it's a cooling graph. gas, gas to liquid, liquid, liquid to solid, solid. So we're told that water is simply freezing. So that's going from a liquid to a solid. So we're only talking about that one spot right there. And of course for that, Q equals ml. Now here's the latent heat of fusion that we use here. And realize, of course, now this is not quite right. This is a mistake here. This should be 1 liter equals 1 kg. Therefore, 2 liters equals 2 kgs. My mistake there. Please fix that up. Because the density is 1 gram per milliliter, therefore 1 kg is 1 liter. So Q equals mLF. So mass. Now the latent heat of fusion for water, we're going to have to look that up on this chart. For water, latent heat of fusion, LF, 3.4 times 10 to the 5. 3.4 times 10 to the 5. But of course, since it's a cooling graph, we have to use a negative there. Use for cooling graphs, because energy is being released as things cool off. And that's going to give us negative 6.8 times 10 to the 5 joules. All right, easy there, just one step. Let's look at the next one. How much thermal energy is absorbed when gold melts? Okay, so that means it's going to be a heating curve. So let's just sketch it out. Solid, solid to liquid, liquid, liquid to gas, gas. And it's melting. And of course, we know melting, that is that region right there. So we're only looking at one region here as well. So of course, Q equals mLF. And of course, that is equivalent to 0.35 kgs. Latent heat of fusion, we're going to use the positive version because, again, it is absorbing energy. So if we look at gold, latent heat of fusion, gold, 1.1 times 10 to the 6. 1.1 times 10 to the 6. So that's going to give us 3.9 times 10 to the 5 joules. Easy, easy. Okay, the next one, I think this is the last one here, and I left room on the next page too. If we've run out of room here, we can take a look there. How much thermal energy is released? Cooling curve. When 500 grams of steam condenses into liquid water and cools to 50 degrees C. Okay, so this is water, so this is one that we know, right? Gas, gas to liquid, liquid, liquid to solid, solid. Gas, gas to liquid, liquid, liquid to solid, solid. And of course, we know what happens with water. It freezes or melts at 0 degrees C and boils or condenses at 100 degrees C. We know those ones. Those ones you kind of have memorized. And if you don't, well, that's okay. Here it is. Melting point of water, freezing point of, or boiling point of water. Just make sure you have them in the right spot. So here we have it at 100. So we have steam. Steam, of course. Gas, it's at 100. So I think we're starting here likely. Condenses into liquid water. Condenses into liquid water right here. So that's that spot. And then cools down to 50. Or as you guys like to say, 50. So it looks like we have two regions here. Steam condensing into a liquid and then cooling down until we're at 50. So we have those two regions there. So we're going to be using Q equals mL, so the vaporization, that's always the upper part of the graph. And then here, we just simply have liquid water cooling, so that uses that. So let's look at gas to liquid. our two areas. Now you can go into the next page if you're running out of room here. I'm going to see if I can kind of try to squeeze it in here. Q equals MLV. So it's 500 grams. 500 grams, of course, is 0.5 kgs. The latent heat of vaporization for water, the LV for water, 2.3 times 10 to the 6. 2.3 times 10 to the 6. But as you guessed it, since it's cooling, we have to put that negative in front of there. So that's going to give us negative 1,150,000. Okay. When it's in the liquid phase, Q equals MC delta T. The mass of water is 0.5. The specific heat capacity of liquid water. Again, we have to go back here to find the C value for water. Now notice, this sheet does have a different one for ice. So if we're using ice, it does have a different value. Water, 4.18 times 10 to the 3. 4.18 times 10 to the 3. And lastly here, our temperature start. So if I'm going from left to right, always read your graph from left to right. Left, 100, 50. Initial temperature is 100. Final temperature is 50. So 50 minus 100. Because remember, delta T is always T final minus T initial. So be careful with that. So when I do that, so I get my 0.5, 4.18 times 10 to the 3, and of course 50 minus 100 is negative 50. That makes sense because I should be getting a negative here, right? Because it's being released. Negative 104,500 joules. Okay, and then here you could go to the next page, I suppose, if you're running out of room like I am, to figure out, okay, what's the total thermal energy now going to be? So total thermal energy. So negative 1,150,000 combined with negative 104,500. Negative 1,254,500. Or I think I rounded it off to 2 sig figs here. Negative 1,300,000. Or in scientific notation, negative 1.3 times 10 to the 6 joules. So you can see how it goes through a few different areas. All right, we just have one more section, one middle video to do here, and then we'll be good.